In this video module, we're going to walk through the different analyses that you can do in the Analysis Workflow module. Our first step within an installation is going to set up the configuration, which means to assign an input path, which is where our cell files would be housed, an output path, which is where the chip files will be written to, as well as a QC history path. After that, we're going to walk through how to do and set up a single sample analysis for CytoScan arrays, then a normal diploid analysis for CytoScan arrays. The normal diploid analysis is something that you would use for cancer samples that have lots of aberrations, and therefore the segment calling may not be correct during a single sample analysis because too much of the genome is non-diploid. We will then walk through how to set up the Mendelian Inheritance Error Check, which is where if you have a duo or trio of chip files, you can compare the genotypes to look for higher rates of Mendelian inheritance errors on given chromosomes. And lastly, we will walk through how to set up an Oncoscan single sample analysis. Okay, so let's go ahead and go into the software and analyze some files. If you're coming from the previous tutorial of installation and library file setup, this is the screen you would see. So there's two ways to launch the analysis workflow. One would be to come up here to Analysis, Perform Analysis Setup, and you can launch the Analysis Workflow module through the browser, or you do not have to have the browser open. You can go to Start, All Programs, Affymetrix, ChAS, Analysis Workflow, and launch it individually without the browser. So if it's the first time that you're setting up the analysis workflow, you'll be prompted to configure the input path. So you can either just say, OK, I don't have that screen up, just say OK, or the same way to get to this screen is to go through Utility Actions, Configuration. And this will allow us to select multiple input paths. So for instance, you may have your cell files for different array types in different folders. You may have an input path that's a larger directory, and then you can select subdirectories underneath that. In this case, I have my C drive CytoScan data already added, but I can add an additional input path if I would like. So for instance, I have a folder here called ChAS3 data. I can select that as well and say OK. So these are my input paths. It just makes it quicker for me to select cell files each time I go in to run an analysis. I then need to select an output results path. This is where the chip files, whether they be CYCHP files from CytoScan or OSCHP files from Oncoscan, and where they will be written. So in this case, I'm using my C CytoScan data as to where my chip files will be housed. And then lastly is to assign a QC history path. This is going to be a text file that captures the QC history, so your MapD and your SNPQC for every batch that you run through the Analysis Workflow module. So as you can see, I've set mine up as a subdirectory under CytoScan data. And so I can change that, or I can leave it as is in this case. So I've assigned a QC history path, so I'm going to go ahead and leave that. And now I click Save. And now my settings are saved, and I'm ready to go ahead and set up an analysis. So we have three tabs up here. We're going to be doing an analysis setup first. And I'm going to choose the CytoScan HD array. I have library files installed for the CytoScan HD as well as Oncoscan, but first we're going to do CytoScan HD. I'm going to select the workflow that I would like to use. We're going to start off with a single sample analysis. For those who have previously used ChAS, this has been probably the primary option that you've been using for your constitutional samples, or for any sample. So we're going to run our single sample analysis. And you can name this workflow if you would like to. We're just going to go ahead and leave the default name as workflow. The reference model file will automatically be selected for you. It's our only option. And as well as the database. And now I can select my cell files. I'm going to click Add. And if you remember, my first default input path was my CytoScan data. So when I clicked Add, the software defaulted to that first input file path. I'm going to go ahead and go to ChAS 3 data and select a constitutional sample. So I double click my cell file. Now you can add as many cell files as you'd like for a particular batch in this window. Single sample analysis just refers to my individual sample here being compared to the reference model file. But you can certainly add many cell files that you have each per batch in this window at a given time, and serially each cell file will be analyzed against the reference model file. Then I can select an output folder. This is the default that I had set, but you can certainly change that. So maybe I want it to go in the same folder that I just selected the cell file from. I can do that and say OK. And if you want to append a suffix onto the end of the CHIP file, you may do that as well. I'll just go ahead and leave that blank, and we're going to hit Submit. And now we flip over to the Workflow Dashboard tab, and you can see the status as this particular sample file is being analyzed. Once the analysis has successfully completed, we can see a green View Results list and View Logs. We'll go ahead and allow this sample to do its analysis so that then we can walk through the QC. Okay, our analysis has successfully completed. So now at this point we can either set up another analysis. We can view the results, the QC results. So we can do that by clicking on this View Results List button. The analysis workflow also allows you to queue up several runs in a row. So I can go to the analysis setup like we did and start a single sample analysis. Then while that's running, go ahead and go back to the analysis setup and queue up some other runs. So here we have our constitutional sample, and we can check the QC settings. So we have our MAPD, SNP-QC. Nothing's highlighted, which tells me that this sample is within bounds, and the threshold test does tell me this. So now I know, okay, great, I can go ahead and move on with this sample and bring it into the browser. So I can do that either by selecting this checkbox and clicking View in Browser, which will then launch the browser if it's not already open, and load the sample. Or you can go to the browser itself and do File, Open, and load this sample directly into the browser. So then you could go on to the module which would be using the copy number data and SNP data for interpreting the sample. But we're not quite done. We're going to go ahead and do a normal diploid analysis. And so let's go ahead and go back to the Analysis Setup tab. We are still using the CytoScan array, but what's different is the analysis workflow. So we're going to set this up the same exact way that we just did with the single sample analysis, but instead we're going to choose a normal diploid. Again, these are going to be for samples that are cancer samples that have been run on CytoScan that have greater than 50% of the genome have an aberration. So if you have cancer samples that you think might fall into this category, you can go ahead and choose the normal diploid analysis. If the analysis finds that greater than 50% of the genome is in fact diploid, it will run the same algorithm that is run with the single sample analysis. But if the genome is 50% non-diploid, then the algorithm will go through, look for those regions that are truly diploid, and center the data based on those regions. If you have run a sample through the regular single sample analysis and go to look at it in the browser and find that the tracks aren't agreeing with the segment calls, and we will look at that after this analysis, you can certainly go ahead and reanalyze that cell file using the normal diploid analysis. And an .nd is appended onto the sample so that you know that this sample has been run through the normal diploid analysis. So we're going to choose normal diploid. It uses the same reference model file and annotation. We'll click Add so we can get our cell file. And this cell file I have in our ChAS3 data. And it's a cancer sample, so I'm going to choose this cancer sample, say Open. And now for the output path, I also want to put this in my ChAS3 data file folder. Say OK. And since the software goes ahead and appends an ND onto this sample, I will go ahead and leave this blank because I will be able to tell the difference between this particular cell file that has been run through the regular single sample analysis and the CHIP file that has been run, that was generated from the normal diploid analysis. And we'll go ahead and hit Submit. And my workflow is off and running. And now again, if I wanted to set up another run, I can just go back to the analysis setup and select more cell files and then hit Submit, and it will just be appended into this queue. You can add several, and it just serially will go through the first one that was hit Submit, and then it will go on to the next analysis. Once this analysis is completed, we will look at the cancer sample that was run in the single sample analysis as well as the cancer sample that was run in the normal diploid analysis to see what the normal diploid algorithm does for those samples that have greater than 50% of the genome being non-diploid. Okay, our normal diploid analysis has now completed. And let's go ahead and view the QC on this one as well. So we're going to go to the View Results list. And here's our cancer sample. It is outside of bounds, and we can see that certain metrics are highlighted under the regular QC. You'll notice that there's the basic QC for CytoScan, which just gives you your MapD and your SNP QC. When you're running a sample through normal diploid, we do recommend looking at the normal diploid normalization view. And you'll see two more metrics. They have the normal diploid SNP QC and the normal diploid waviness SD. And it gives you the threshold here of, again, just like SNP QC being 15, the normal diploid SNP QC being 15. By the algorithm going ahead and detecting and just using those regions that are normal diploid within the sample, we can see that the SNP QC does meet our threshold of 15. It is almost 19. And the waviness SD is 0.11, so below our R.12. So for a normal diploid sample, we're happy because we're looking at the normal diploid values and they are meeting our thresholds. So we can go ahead and look at these in the browser. Again, we can click on the sample and choose View in Browser. But since I want to load the ND, the normal diploid version of this cell file, as well as the regular SSA, let's go ahead and minimize the analysis workflow for now and go to File, Open in the browser. And I want to load these two CHIP files to show what the normal diploid algorithm does for cancer samples where 50% of the genome is non-diploid. My ChAS3 data, and here I have my cancer sample 01 and then my cancer sample 01 with the ND, so I can tell which one has gone through normal diploid. I'm just going to hold down the Control key, highlight both CHIP files, and click Open. It's letting me know that they failed QC. And we know that from the SSA algorithm. When it was run, we saw that the SNP QC was, I believe, while that's loading, we'll go ahead and look. I believe it was 8. So yes, 8.36. And so that's what the browser is looking at. It's saying, oh, this sample is outside of bounds. But we're going to go ahead and load it anyway because we've looked at our QC and we know that the normal diploid is meeting the thresholds that we would like to see. So back to the browser, and when these samples load, we're going to first look at the SSA, so the single sample analysis version of this particular file, and then we'll go ahead and look at the the cell file when it was run through the normal diploid algorithm. Okay, we're going to go ahead and turn off the pink track, which is our normal diploid algorithm ChIP file, so that we can concentrate on the single sample analysis. So if we run this sample through our single sample analysis, we can see that there's no segments really being called, a couple little ones. The log2 is centered around the 0 line, but the allele difference track is showing 4 peaks. And usually for diploid, we'd be seeing 3 tracks. So our 4 tracks are AAA, AAB, ABB, and BBB genotype calls. So this tells us that something isn't quite right the way the algorithm is calling it, because so much is going on in this sample, as we can tell from the carrier view up top. If we look at chromosome 2, we see something very similar to what we saw in chromosome 1. We're seeing 4 tracks and no segments being called. If we look at chromosome 14, here we see that a loss is being called along the length of chromosome 14. The log2 is shifted downward, but we are seeing 3 tracks. And those 3 tracks being AA, AB, BB. So we know that there's no way that we can actually truly have a loss and have 3 SNP tracks. So let's see what happens if when we go to this exact same sample but run through the normal diploid algorithm. So now I'm going to turn on that sample, and we'll go back to chromosome 1 so that we can look at the difference. Here we have both our samples, the pink being the normal diploid algorithm and the purple being the algorithm, the cell file being run through the single sample analysis, the one that we already looked at where we saw no segments really being called, but yet 4 tracks. Now let's go back up, let's go to the top, which is the sample run through normal diploid, and we can see we have a gain segment called roughly the whole length of chromosome 1. The log2 is now shifted upward, whereas on this sample it was centered around 0. We now see it shifted above the 0 line and 4 tracks. So now the graphs and the segment call are matching what we would believe to be for a gain. Let's go ahead and go to chromosome 14. Now if we remember from the bottom, again, this is what we saw earlier where we had 3 SNP tracks, but it was being called a loss. Now, run through the normal diploid algorithm, we still have our 3 SNP tracks, but the log2 is now centered around the 0 line like we would expect for a truly diploid chromosome, and the segments are not being called for the length of the chromosome. So this is the benefit of running the normal diploid algorithm when running cancer samples, is that it will recenter the data so that the segments match, the segment calls will match what the graphs are telling you in the data. All right, so let's go back to the analysis workflow and finish the couple steps we have left. The next one we're going to talk about is the Mendelian Inheritance Error tool. So again, we're going to go to Analysis Setup. This is available for CytoScan arrays, so I'm going to choose my CytoScan HD array. The last thing we ran was Normal Diploid Analysis, so now I'm going to choose the Mendelian Error Check. This is going to change our screen. We're going to be asked for ChIP files, so CYCHP files already run through the algorithm. Now again, you can run this as a duo as long as you have the child. So you need a child ChIP file and either a mother or a father. There is a quick gender check, so you will see an error if you assign a male for the mother or a female for the father. Or if you have all 3, you can assign the ChIP files for all 3. So we'll go ahead and run all 3. I'm going to click on my 3 dots here, go to my ChAS3 data, and the child is this file, and say open. And now I'm going to select the mother, and then select the father out of that same folder. By default in the library file, we do provide an allele frequency file. This can be a custom file. If you decide that you think you need to make one, by all means, you can make a file for this. And then select the analysis output name. When I selected the child, the output file, which will be a text file that can be opened in Excel, will automatically be named the child, the CHIP file assigned as the child. So it's going to, the default is to save this file under users and then my login. And I'm going to go ahead and add that to the same folder where the data is, my ChAS3 data file, and say save, and then submit. This is a very quick analysis. As you can see, it's running in our analysis workflow, and it only takes about a minute or so. So once this analysis is complete, we're going to open it up in Excel so that we can see what's provided by the Mendelian Error Check. Okay, the analysis is complete. And you can go ahead, and if you click View Results, it will ask you if you want to open it, and it opens it in Notepad, which is not quite as easy to read. So we're going to go ahead and go to Excel. And choose File, Open. ChAS3 data, and then here is my proband text file that I can now open in Excel and look for two things is what the report's going to tell us. It's going to tell us relatedness. So the samples that we assigned as mother, father, and child, are they truly related? And also, on the chromosomes, was there a particular chromosome that had a higher rate of Mendelian inheritance errors, which might indicate an instance of UPD. So here it tells us the sample key 0, 1, and 2, so which one was the child, the mother, and the father, the CHIP files that we assigned. And here's where we see relatedness. So this column that says role validity, if you have a 1 in that column, that is telling us that yes, these samples, by comparing their genotypes, are related. If you see a 0 in any of these, that will let you know that that sample is not related to that trio. So there's our relatedness. And now we come down here, and this will tell us our chromosomes which may have a higher rate of Mendelian inheritance errors. So we have chromosome 1 through 22 and X. These are the number of genotypable markers on each one of those chromosomes. Here's the Mendelian inheritance error within that trio. So there were 119 errors within the 56,000 markers. It gives you the error rate for mom and dad. And these are just the raw numbers. These are then converted into a percentage in the next 3 columns. So we have percent trio, and then for the mother and the father. And again, this is just a percentage by taking for this error rate, the 119 and dividing it into the 56,482. So there is, understandably, a low level of Mendelian error rate. We would expect that. But what we're looking for is a jump. So here you see all these samples pass, they're within bounds. And so you're seeing about 1/4% of error rate, which is what one would expect. Then on chromosome 15, we see this jump to almost 7%. So what that's telling us is that chromosome 15 among this trio has a high rate of Mendelian inheritance errors. And when we look to mom and dad, we can see that mom has has no errors whatsoever, 0%. So what that's telling us is that the chromosome 15 of the child came from mom. Both chromosomes came from mom, whereas the father has a very high rate, again around almost 7%, showing that his chromosome 15 isn't represented in the child. So the trio tools is a nice way to check to look for chromosomes or large regions of chromosomes that maybe have a higher rate of Mendelian inheritance errors, indicating potentially regions of UPD. You can then take these CHIP files and go into the browser and certainly look at the actual genotypes and compare the genotypes between the mother, father, and child. Okay, lastly, let's go ahead and go on to Oncoscan in terms of the analysis workflow. We're going to go back to the analysis setup and choose Oncoscan. And now Oncoscan as an array is a little different. It has 2 cell files for every sample. So we're going to select the analysis workflow that we want. Most commonly, we'll probably be using this FFPE analysis for your samples. If you, or when you run the control, the Ref103 control, you will want to select the Ref103 analysis, as it uses a different reference model file that's more applicable for a blood sample or a cell line sample. But if you're running tumor from FFPE, you want to choose the FFPE analysis. And the reference model file is automatically selected for you. Since I have FFPE, it's giving me the FFPE reference model file. Automatically selects my database and my somatic mutation reference model file. And then in the library file, it provides the somatic mutation threshold file, which was automatically selected as well. All right, we want to add our cell files. So we're going to add the cell files either for the AT channel or the GC channel. So we'll do add cell files, AT channel. We're going to go to my ChAS3 data folder again. And now I'm going to go to my Oncoscan data. And so here I have an A sample indicating it came from AT, and down here as well, this A indicating it was an AT channel. So by holding Control, I can highlight both and click Open. And now I'm going to do the same thing, add cell files for the GC, and choose the other 2 cell files, the :_C, and then the _C here in liver. All right, you do want to make sure that they're lined up properly, that the AT channel is lined up with the GC channel. And so I have sample O1 liver A and sample O1 liver C. So my columns are aligned properly. And then I can choose a results file name. Now I can say auto-generate my name. And now the auto-generate name looks for the root word or the root name of the cell file to be the same between the A channel and the C channel, except for the last letter or number. And so in this case, since everything matched in these 2 samples up until the A and the C, it automatically went ahead and said, this is what I'm going to name your OSCHP file, the root name. So great. It didn't do that for the sample above because the only difference is in the middle of the name. It's not that last letter before the dot cell. And so once it got to _A and _C, it said, you know, these root names don't match, so I'm going to name it output. You can certainly leave it as output, but that might get confusing. So what I can do here, I can either go back, rename my cell files, or here I can just double click in this space and say that I want to name it :sample 05. And now I can choose an output folder. I'm going to go ahead and put it in that Oncoscan folder as well. Okay. And if I wanted to append a suffix to the OSCHP file names, I can do that as well. You can also do import a batch file, so basically a tab delimited file with the AT channel cell file names, the GC channel cell file names, and the name that you would like it to have. And you can read about how to do that in the ChAS 3.0 manual. So in this case, we went ahead and set up our cell files, and we're going to go ahead and hit submit. And now again, we go back to the workflow dashboard, and the analysis is off and running for these 2 files. So once this analysis is complete, we will walk through the QC on the Oncoscan files. Okay, our Oncoscan analysis is complete, so let's go ahead and view the results. Here's our 2 samples, and we can see that they are both within bounds. Our MAPD is less than the threshold of zero 0.3, the ND SNP QC is greater than our threshold test of 26. And the cell pair check status is passed. What this will tell us is that we did indeed match up the correct AT channel with the correct GC channel. So that lets us know that we did indeed pair them correctly. And then we also see some of the Tuscan algorithm metrics as well, such as low diploid flag, means that flag was not thrown. It was able to find enough normal diploid within these samples. So that's excellent. And it was able to figure out the percent AC fraction, or aberrant cell fraction. You may also hear it called tumor burden. And the ploidy for these two samples was 2. That's the basic QC. There's a detailed QC as well, which gives a few more metrics. Or you can set up your own custom metrics as well. And again, please refer to the manual on how to create your own QC metric view. Lastly, what we can do with these samples is, and this applies for CytoScan as well, you can generate reports. You can export the probe level data, or down here there's the copy number expression overlap report. This is also part of the COMAP software solution, and there's a separate video on how to use our TAC software with ChAS as our COMAP solution. So please refer to that to see how to run the copy number expression overlap report. There's also the gene report that can be exported from this window as well, which is a report that can be opened up in Excel, which will give you the copy number for a given gene, and we do provide the 900 Oncoscan genes. Or for CytoScan, we do provide a list of from the developmental delay genotype to phenotype bed file list. Or you can certainly put in your own custom list. If you have your list of favorite 10, 15, 500 genes that you want to know for these given samples what the copy number is, you can certainly import those as a bed file and run that analysis and get that output. Again, for details on that, see the ChAS 3.0 user guide. So that concludes what we wanted to go through on the analysis workflow module. We now know how to convert cell files to CHIP files, whether we're using the single sample analysis, the normal diploid analysis, or Oncoscan files, cell files, as well as how to run the Mendelian Inheritance Error Check. Thank you.